Imagine a machine built in the 1970s, the era of 8-track tapes and rotary phones. Now imagine that same machine is still driving through the dark, billions of miles off the map, and it is still calling home. To understand how it got there, we have to go back to 1965. A graduate student named Gary Flandreau was working at NASA's Jet Propulsion Laboratory, and he was given a daunting math problem: find a route to the outer planets. This map shows how the planets were positioned back then. Flandreau discovered that during the late 1970s, Jupiter, Saturn, Uranus, and Neptune would all move on to the exact same side of the Sun. An alignment like this only happens once every 176 years. If you launched a probe at exactly the right time, you could draw a single continuous line from Earth to all 4 giant planets. You could visit the entire outer solar system in one trip. Because of that moving planetary window, NASA suddenly had a strict deadline. They had to design, build, and launch a pair of twin spacecraft before the planets drifted out of position. In late summer of 1977, Voyager 1 and Voyager 2 lifted off. The biggest problem with visiting the outer planets is gasoline. Rockets in the 1970s simply could not carry enough chemical fuel to push a heavy spacecraft all the way to Neptune. The solution is a maneuver called a gravity assist. As this animation shows, instead of firing engines, the Voyager probe approaches a heavy planet like Jupiter from behind, riding right along the planet's own path around the Sun. As it gets close, the planet's powerful pull grabs the spacecraft and yanks it along. The probe steals a tiny fraction of the planet's orbital energy, accelerating around the curve and shooting outward at a much higher speed. Voyager 2 performed this exact slingshot maneuver over and over again. It bounced from Jupiter to Saturn and then to Uranus, multiplying its speed with each successful catch and release. That stolen momentum provided the exact speed needed to complete the planetary tour. That velocity also gave both probes enough energy to eventually leave the grip of the Sun's gravity and head into the stars. Out in the deep freeze of space, solar panels are useless. The Sun is too far away to provide energy, which raises a serious question. How do you keep a machine alive and running in the dark? This gauge tracks the spacecraft's dropping power. Powered by the decaying heat of plutonium, the available electricity shrinks year by year. To survive, engineers ration the dwindling supply, permanently switching off heaters and instruments. Today, Voyager runs on less electricity than a standard microwave. Then there is the challenge of calling home. Voyager transmits its data back to Earth using a 20-watt radio, about the same power as a refrigerator light bulb, broadcasting from over 15 billion miles away. For comparison, the phone in your pocket communicates at tens of millions of bits per second. Voyager trickles its information back to us at roughly 160 bits per second. To catch that incredibly faint whisper, NASA relies on the Deep Space Network. These giant antenna dishes are positioned around the world to constantly listen for Voyager's signal. The mission survives today entirely through this daily balancing act. Ground controllers carefully ration a fading battery, while giant dishes on Earth strain to hear a signal quieter than the background noise of space. By 1990, Voyager 1 had flown past all of its planetary targets. Before engineers shut down the cameras to save power, astronomer Carl Sagan campaigned for one final, scientifically unnecessary request. He asked NASA to command the spacecraft to swivel its camera platform backward into the dark to photograph Earth from 3.7 billion miles away. In the resulting image, Earth occupies less than a single pixel. It is a tiny speck of pale blue light caught almost by accident in a scattered ray of the Sun. Looking at our entire world reduced to a solitary dot changed how people viewed the mission. It turned a significant engineering achievement into a quiet reminder of human vulnerability, and the fact that everyone we have ever known lived out their lives on that one tiny speck. With their cameras permanently powered down, the 2 blind probes kept driving outward, heading toward the uncharted edge of the solar system. As this diagram shows, the Sun blows a giant protective bubble of particles that surrounds the planets. But eventually, the wind from our Sun runs out of steam and crashes into the cold pressure of deep space. At this final physical border, known as the heliopause, our solar system ends, and the rest of the galaxy begins.
In 2012 and again in 2018, the probes detected a sharp jump in the thickness of the space around them. They were finally swimming through the dense sea of particles that fills the gaps between stars. They had successfully crossed the border and entered interstellar space. These two machines, built with the technology of the 1970s, remain the farthest human-made objects in existence. Eventually, the last of the plutonium will cool, and the computers will shut down for good. But the physical probes, along with the golden records bolted to their sides, will drift indefinitely, a silent, permanent monument to humanity traveling among the stars.